Let's look at problem 2302. Count subarrays with score less than k. First, I would say this problem is quite similar to problem 1695. So here we are going to provide a solution using the two-pointer sliding window method. First, I'll go over the statement of the problem, and then I will look at one example and specify the main idea. So lastly, we will give the code and run the special cases and generic cases. So finally, as an extra piece, so I will explain why the method works. So first, let's look at the statement of the problem. So here, first, it defines the score of an array. That is the product of its sum and its length. For example, this one, it has sum that is 15, and its length is 5, so the score is 75. So the problem is that given a positive integer array nums and an integer k, so we are required to find the number of non-empty subarrays of nums whose score is strictly less than k. So here it emphasizes strictly less than k. So here we are considering subarray, so not subsequence. So let's look at the constraint of the problem. So the first constraint tells that the nums is not empty and its length can be up to an order 10 to the power 5th, which means we should avoid using brute force to solve this problem. So second and third constraints are about the range of the elements in nums and the variable k. So with that said, let's look at one example. So before we look at this example as a routine, let's specify the method we are going to use. It's the two-pointer sliding window method. And here the condition is that the sum of the subarray times the length is strictly less than k, right? So this is the condition. And the main idea is still the same. So for each index, let's call it r, so we can understand this r as the right pointer. Then we try to find the number of subarrays ending at this index r and satisfy the condition. Satisfy the condition. So let's comment this line. So once this is done, we just need to add up together the numbers. So the thing here is how to effectively check the condition. Right. So actually, up to now, this is sort of routine. Basically, we can use a partial sum variable to do the job. So with that said, let's look at one example. Let's look at example 1, which should be insufficient. So here, so this nums has length 5. So for index I from 0 to 4, right? So for each of the index, we want to find how many valid subarrays ending at that index. Then we just add up the number of subsequences. For example, for I equals 0, so we get 2, right? So this just corresponding to one of the subarrays. So this gives 1, contribute 1 to the final result. When I equals 1, so we get 2, 1. And because 2, 1 add up together, so we get 3. 3 times 2 is 6, less than k. So this contributes to 2 subarrays. The reason is that the starting point index of an array can be any position in this one, right? For example, it's starting here and it's starting here. Anyway, it needs to be ending at index at this number 1. So we get 2. For I equals 2, we get 4, ending at 4. So we cannot add 1 here, because if we add 1, the length is 2, and 2 times 5 is 10. It's equal to 10. But the problem requires to strictly less than 10. So this contributes to the final result by 1. So when I equals 3, so we get ending at 3. So 3, right? So we cannot add 4, because if we add 4, 3 and 4 sums to 7, and 7 times 2 is 14, greater than 10. So again, we get only 3. So this contributes to the final result by 1. So now let's look at I equals 4. So then we get 5. Similarly, this contributed to the final result by 1. So you sum up these numbers together, you get 1, 2, 1, 1, 1. So the return will be 6. So that's a quick walkthrough of the idea and the methods we're going to use. Now let's realize this procedure using the two-pointer. So again, it's the same as problem 1695, just using check and update procedure. So for this purpose, let me first make some preparation. Step 1. So preparation. So we'll initialize a variable called result, which is the one we're going to return its final state. And also we use a partial sum to track the running sums. So the partial sum is initialized to be 0. And then we specify the left pointer. Originally it's 0, the index 0. So now we iterate for the right pointer. So for r, let's call it r, and y, enumerate nums. So the first step, let's say, is basically check, right? So for the partial sum, we just update it. Partial sum, we increment by y, the current number. Then we do the check. What's the condition to check? So we check if the current index minus L plus 1, the length of the array from the very left boundary, times the sum. The sum is the partial sum, right? If this is greater or equal than k, right? If this is greater or equal than k, we need to push the left pointer to the right. So if we do so, the partial sum is decremented by nums L, and this corresponding to move the left pointer by 1, right? So once we are out of this check and this while loop, so we are finding an index, let's call it L0, L0. So from L0 to the current R, let's call it R0. So this this piece of subarray, it has sum times the length is strictly less than k. So as such, so the subarrays ending at this current index r contribute to the final result by the amount of this. So it's r minus L plus 1. It means that the corresponding subarray can start at any position but ending at current r, right? So now once we are doing this, we are good to return the final result. Step 2, we're going to return the result, right? That's a simple realization of the two-pointer sliding window. Let's check some special case. So this passed the first one. Let's look at the second one. So corresponding to 1, 1, 1, and k equals 5. So we'll get the result is 5. Now let's we can print out the for at each index how many contributions we get. In other words, how many valid subsequences ending at that index and satisfy the condition. So we can print. So at index, let's see, R, ending at index R. So the contribution of the subarrays, that is R minus L plus 1. So let's print out this. Let's do for this example, because we use this example to analyze the problem. So when k equals 10, so yeah. So the contributions of this is 1, 2, 1, 1, 1. Same as here, 1, 2, 1, 1, 1. So now let's check the generic case. So we submit. Yeah, it passes the all the test cases. So here actually up to now we have a problem. That is, so in this for loop, so if we move the right boundary from R to next R, how can we make sure that the L should be no less than the previous state of L? So here I want to analyze a little bit this part, but you can stop here if you do not want to understand the finer details. Extra point. So yeah, after this loop, so we are basically finding a piece from L naught to R naught. So let's assume this piece of subarray has sum S and the length L. So we know that this condition holds here. So that is S times L is less than K, right? So this is after the while loop. And also another one is that assume the corresponding number corresponding, let's see, called Y is the L naught minus 1. So we also know that S plus Y times L plus 1 is greater or equal than K, right? This is the same after this while loop. Now if we look at R naught plus 1, so we claim that the left boundary L satisfies the condition of the problem is such that L is greater or equal than the L naught, in other words, the previous state. So in other words, in the while loop, we do not need to restart L from the very beginning. So why? So we can see this problem like this. So in order to show this, we can assume if L is if L equals L naught minus 1, and the corresponding numbers, let's call the corresponding numbers L naught minus 1, by assumption it's not negative, right? Then this one from the subarray from L naught minus 1 to R naught plus 1, it has a length that is the total length is R naught. It's S actually it's L plus 1 plus 1, and the sum is s plus y plus the corresponding number. Let's call it nums l naught minus 1. So if we check the condition, actually what we have is l plus 2 times s plus y plus nums l naught minus 1. So this is greater or equal than the l plus 1 times s plus y, so which is greater or equal than k. Therefore, we have shown that the new state for the left boundary must be greater or equal or equal to the previous state, which actually validates the method. So the last part of the extra point is sort of some finer details, which you do not need to pay special attention if you don't want to. I think up to now that's it. Thank you very much.